For section 1.3, we're looking at complex numbers. You may have seen these in a high school course. You may not have. We're going to be dealing with that number I, that lowercase I. Complex numbers have the form A plus B I. It's a little lowercase I, where A is your real component and BI is your imaginary component. That says imaginary. I is defined as the square root of -1. So you were told, don't take the square roots of negatives. You can't do it. You technically can. It just requires a different idea of what a number is, or not really a different idea, a more expanded idea. So complex numbers encompass both the real and the imaginaries and combinations of those. Don't worry about drawing this, but if I were to consider the real numbers here, the imaginaries here, they don't have any overlap themselves, but altogether, they are complex numbers. So real numbers really are complex numbers. Imaginary numbers really are complex numbers and combinations of them. Now, what's interesting about I is that it actually has a cycle to it when we raise it to higher and higher powers, which we don't really see in the real numbers. And this cycle goes every 4. I to the first is just I. Nothing crazy there. Anything to the first power is itself. I to the second, well, off to the side here, let's think about this. If I is the square root of -1, raising that to the second power, square root squared, they get rid of each other. I squared would be -1. That's a little funky. We square an imaginary number and we get a real number out of it. I to the third, well, let's think about it. I to the third, I'm going to think of as I squared times I. That would give me 3 i's total. But I just figured out that I squared is -1. So this would be -1 times I, which would be -I. I to the fourth is the really weird one. Let's consider I to the fourth. I to the fourth, let's split that into I squared times I squared. But I just figured out from before that each I squared is a -1. So this is -1 times a -1. -1 times -1 is 1. So I to the fourth is +1. That's very strange, because here's what this means. And again, don't worry about writing this down, but we'll look at some of this stuff later on. If I go one more higher power, that's it for the cycle of I. If I did I to the fifth, I can think of that as I to the fourth times another I. But I already know that I to the fourth is 1, so 1 times anything, that doesn't really matter. I'm just left with I. So I to the fifth is the same thing as I. That's bizarre. And the cycle keeps going. You basically, any higher power just keeps cycling through the cycle of 4. So I to the sixth would be the same thing as I to the second. I to the seventh, same thing as I to the third. I to the eighth, same thing as I to the fourth. And then the cycle repeats. So again, I to the fifth was the same thing as I to the first. And then if I even went higher, 9, 10, 11, 12, they go right back to that cycle of 1, 2, 3, 4. which is a very strange process. It just keeps repeating. But again, we'll get into some example problems on that a little bit later. Okay, so let's first start talking about how we write imaginary numbers and more generically complex numbers. I'm only going to do this on this first problem, and then we're going to kind of see the pattern here. I can think of the square root of -48 as the square root of 48 times the square root of -1. I can split it up. Well, the square root of -1, again, we decided to call I. Square root of 48, you've done that before. That I can do like a factor tree with. Maybe you break it into, I don't know, a 4 and a 12. Maybe the 12 you break into a 3 and a 4. I have a pair of 4s, which means I can bring the number 4 out. The 3 did not get paired up. So, and again, this is stuff you've done before. So square root of 48 is 4 root 3, but I also had that I on there. So 4 root 3 I. Now, just so you know, sometimes some people like writing it this way. Some people like putting the I in front of the square root. That's fine. Either one, whatever you prefer. So the main drive of this first problem was to show that here's basically how we deal with the square roots of negatives. If we have the square root of a negative, extract out an I, and then you've dealt with the negative part of it. So on letter B, to deal with that square root of a negative, I'm just going to call this root 6, and then I'm going to bring out an I. Square root of -10, I'm just going to say root 10, and then bring out an I. So now if I multiply together, remember I can multiply square roots together. So this is going to be negative square root of 60. I times I is I squared. But going back to our cycle of I squared is -1. So this turns into negative root 60 times -1. So the two negatives cancel out, and I'm just left with root 60. And then from here, you can simplify the radical by doing a factor tree. Maybe you break it into, I don't know, a 3 and a 20. 20 you can break into 2 and a 10. 10 I can break into a 2 and a 5. So I've got a pair of 2s. So that'll be 2. I did not pair up the 3 or the 5. So they get multiplied and left in 2 root 15. And that part should be review. So I'm not going to keep going through that. I'll just give you the reduced form, but you're making a factor tree to reduce your radical. For letter C, the first thing we always have to do is deal with that square root of a negative. So I'm going to pop out an I on top. So this is going to be root 63 I over root 21. Just like I can multiply radicals together, I can also divide them if they're both in radicals. If you divide 63 into 21, it's conveniently 3. Still got an I to carry along, and there's nothing else we can do with that one. On letter D, I'm going to extract out the I. just like with anything else, I can cancel them out because I got them on top and bottom. Now, 80 and 125 don't really divide nicely into each other. So another method I could use is I could simplify the top and the bottom. Root 80, if you do your factor tree, root 80 becomes 4 root 5. Root 125 becomes 5 root 5. The root 5s can cancel, and I'm just left with 4/5. For letter E, again, I've got the square root of a negative. So I know that's going to bring out an I. So if I do a factor tree on 128, if you break down 128, it'll turn into 8 root 2. But again, there's also an I here. This is going to be 8 root 2 I all over 4. Now here's where you got to be careful. And this is getting us building into using quadratic formula, which we'll be doing on the next section. I need to think of this as two fractions. I call this heart reducing. This is negative 8 over 4 plus 8 root 2 I over 4. So I've got to think of that 4 being over both of them. I'm basically splitting this into two fractions. Then I can reduce, so negative 8 over 4, negative 2. The 8 and the 4 here will reduce to a 2, so I'll end up with 2 root 2 I. That is in standard form, by the way. Standard complex form is the real part, followed by the imaginary part, which is what we just did. Similar logic on letter F. Again, I know since I have the square root of a negative, there's going to be an I. If you break down root 18, it's 3 root 2. And again, since it was the square root of a negative, I know I'm going to bring out an I. And now a similar logic, I'm going to split this. I'm going to do this heart reducing. It makes kind of like a little heart on here. Negative 3 over 24 plus 3 root 2 I over 24. And then I can reduce each fraction. This will be negative 1/8. Again, the 3 and the 24 will reduce down to an 8. So I'd have root 2 over 8. And I'm just going to stick the I behind it because that's more of what the standard form looks like. Remember that the root 2 and the 8 cannot reduce. You can't reduce that because the 2 is in the square root. I'd have to have the 8 in the square root to be able to reduce. So that is the final answer. So that's getting us a little feel for how to express complex numbers. Now that we have this idea, we have to learn how to do operations on it, like multiplying, adding, subtracting, dividing, all that fun stuff. Good thing is adding and subtracting is just a matter of combining like terms. Think of the I almost like a variable X. If I'm subtracting, these are really two complex numbers I'm subtracting. That's a complex number, that's a complex number, and I'm subtracting them. Basically, like you might think you're going to do, I'm going to distribute the negative through here. So this will be 2 plus 5i plus 6 minus I. Combine like terms. 2 plus 6, 8. 5i minus I, 4i, and I'm done. So adding, subtracting, very simple. Multiplying complex numbers, which basically squaring it is multiplying it by itself, so it still is multiplying, is going to amount to a FOIL. where I have to multiply two things together. So I'm going to write this out, 4 minus 2i times 4 minus 2i. If I multiply the first together, 4 times 4, 16. Multiply the outers together, that's going to be negative 8i. Multiply the inners together, that's going to be another negative 8i. Now be careful on the end here, here's the kicker. Negative 2 times negative 2 is going to be positive 4. And it's I times I, which is I squared. But remember, I squared is negative 1. We learned that at the top. So positive 4i squared is actually, that's actually minus 4, because I'd replace I squared with a negative. So now I have 16 minus 4, so 12. And then negative 8i minus 8i would be minus 16i. Letter C is a kind of a special case with multiplying. These two numbers are called complex conjugates, which you can see here we're going to talk about in just a second. A conjugate basically just means the sign in between is different. That's the only thing different. I'm still going to do this with FOIL, just like I did on the previous problem. First times first, it's going to be 9. Outers, that's going to be 21i. Inners, that's going to be minus 21i. And then last times last, again, be careful here, it's going to be negative 49i squared. Just like on the previous problem, I squared is negative 1, so negative 49 times negative 1 is actually going to become positive 49. So that changes to positive 49. So if I combine the 9 and the 49, that's going to be 58. But here's the important part to note on this. The imaginary parts canceled out with one another, 21i minus 21i. So I was only left with the real part. So I multiplied two complex numbers that had i's in them, but I ended up with just a real number. That's an important concept because that is what the complex conjugate is important for, and it's going to help us with division. So the complex conjugate is if I'm given a plus bi, so some complex number. The complex conjugate is a minus bi. Again, just the sign in between changes. The sign in between changes. So that means if it started out as a negative, it would switch to a positive. Now, why is that important? That is going to help us with division. So we dealt with addition, subtraction, multiplication. Division is kind of funky. There is no such thing as like long division when we're dealing with these weird complex numbers. To deal with dividing by a complex number, we actually multiply by the conjugate on top and bottom. So what do I mean? My denominator is 4 minus 2i. I'm going to multiply top and bottom by 4 plus 2i. So basically, I'm just changing the look of it. I'm multiplying it by something divided by itself. So I'm really multiplying by 1. But what this is going to do, I just saw that multiplying by a conjugate on the bottom here is going to get rid of the i's. So basically my whole goal here is just don't have I in the denominator. All right, so across the top, I'd have to do normal FOIL. So I'd have to multiply 2 plus 3i, 4 plus 2i. If you multiply those out, you'd end up with 8 plus 4i plus 12i. And I'm going to go 2 steps at once here. The last times the last would be plus 6i squared. We know that I squared is going to change the sign. On the bottom, I know that the middles are going to cancel one another out. So really, I don't have to do them. So here's what I mean. I'm going to do 4 times 4, 16. I know the outers would be 8i, the inners would be negative 8i. They're going to cancel one another out. So I'm going to end up with 16. And then if I do last times last, that would be negative 4i squared. That I squared is going to switch the sign, positive 4. So let's see what I have here. I have 2 on top plus 16i. And it's all over 20. Now to put it in standard form, like we did a few problems ago, I'm going to heart reduce it. So 2 over 20 is 1 over 10. 16 over 20 is 4/5, and I still have the I on there. That would be the standard form look for that problem. Similar logic on letter B. If I'm dividing by a complex number, something that's got I in it, that really amounts to multiplying by the conjugate of the denominator. So that's going to be 1 minus I. So across the top, again, that's regular FOIL. You'd end up with 1 minus I minus 3i. Again, be careful on doing the last. You'd have positive 3i squared, but that becomes minus 3. On the bottom, again, since they're conjugates, I really only have to multiply the first times the first. So 1 times 1. The last times the last. That would be negative I squared. That switches to positive 1. Again, I'd have negative I squared, but again, I squared is negative 1, so I'd have negative negative 1, which becomes plus 1. So across the top, that's going to be negative 2 minus 4i. Bottom is just 2. Now I can heart reduce. Negative 2 over 2 is negative 1. Negative 4i over 2 is going to be minus 2i. Letter C is a little bit tricky looking because it's actually simpler than the other ones. That really is a complex number on the bottom, I, so I can just multiply by the conjugate. Now here's where it gets tricky. The conjugate is actually just negative I. Think of I, well, that just means that the real part is 0. So think of I as 0 plus I. Its conjugate, therefore, would be 0 minus I, which really is just negative I. So my conjugate, my complex conjugate of I is actually just negative I. So I'm going to multiply, oops, that's an I. I'm going to multiply top and bottom by negative I. Again, these are being multiplied. So across the top, that's going to be 5i On the bottom, I would have negative I squared. Negative I squared is positive 1. So really this becomes 5i. The last concept we're going to talk about with this section goes back to that idea of the cycle of I. So I to the 34th, here's how I want to think of this. I know that every I to the 4th is 1. I know that I to the 34th has a lot of I to the 4ths in it. And let's think about how many it would have. Well, 34, if I divide by 4, that's going to give me 8 with a remainder. So I'm going to have I to the 4th 8 times. Imagine me writing this 8 times. I'm not going to actually do it. 8 times of that. But each one of those I to the 4ths really doesn't matter. Each I to the 4th is a 1. So it's 1 times 1 times 1. None of those really matter. All that matters is what's going to be left over. So here's how we're going to attack these. If we've got I to a big power, we're going to divide by 4, because we know every 4 i's is just going to become the number 1. And we're going to go very old school with our dividing here. And I'm actually going to write remainder 2. Again, what is this saying? This is saying that I to the 34th is I to the 4th 8 times over. But every single one of those is the number 1. 1 times 1 times 1. So who cares? What matters is that there's a leftover I squared. So really, I to the 34th is the same thing as I squared. And we decided that I squared already was negative 1. So here's how we're going to do these problems. We're going to divide the power by 4. The remainder becomes the actual power. So let's do it one more problem here. I'm going to divide 63 by 4. And again, we're going to go very old school in our dividing here. So it's going to go in there once. And again, what really matters is the remainder. So this is telling me that I to the 63rd is the same thing as I to the 3rd. We determined from above that I to the 3rd is negative I. For the last one, again, divide by 4. Now you could go through long division, but hopefully you know that 100 divided by 4 is 25. More importantly, it goes in there evenly, so the remainder is 0. Well, how do we deal with that? Well, we do the same thing we did on the other ones. The remainder will become the power. Anything to the 0 power is 1. And we're done.